Hi, I'm James Kirk from the Center for Integrated Cognition, and I'll be talking about our work improving knowledge extraction from large language models for task learning through agent analysis. Cognitive agents often need to acquire knowledge. There are many available knowledge sources, from curated knowledge bases like Psych to semi-curated knowledge bases to instructors and natural language artifacts like documents and books. The question is, where do large language models fit, and can they be an effective and reliable source of knowledge for agents? A brief outline. First, I'm going to introduce prompting for task knowledge. Then I will discuss requirements for embodied learning, followed by a description of STARS, the learning process implemented in this paper, and finally conclude with a demonstration and results. First, we will discuss template-based prompting for prompting for task knowledge, which is used as a baseline. The context here is a robot that is trying to learn a task. The first part of the template is a prompt example, as in one-shot prompting. And here the task is to deliver a package along with some context. And the information that we're trying to retrieve from a language model, which is a simple series of steps for the agent to perform, as well as the goal. In this case, that the goal is that the package is in Gary's office. This prompt example is followed by a template that the agent can instantiate with the task that it is given along with context. So for example, if you have an agent, a robot in this case, that has been given the task to tidy the kitchen, it can also fill the template with context that it knows, such as where it is in the kitchen, and an object that it sees, a paper cup on the table. The response that we get from the language model for this prompt is to pick up the paper cup, put the paper cup in the trash can, and the goal. The goal is that the paper cup is in the trash can. And so the template here is trying to influence the language model to generate the content that is desired, which is a simple series of steps of actions to perform, along with a goal description, as well as the form that the agent is trying to get, which is language that is interpretable by the robot. But unfortunately, even with good prompt examples, this doesn't ensure that the language is, for example, interpretable by the robot. And in fact, there's a number of requirements that are particular to an embodied agent that is trying to learn task knowledge. Responses retrieved from a large language model for embodied agents must be interpretable. The agent must be able to interpret the responses using its natural language processing capabilities. It must be groundable to the situation. The objects and relations and features referenced in the response must be perceivable and groundable by the agent. It must be compatible with affordances and embodiment. Large language models are generally trained on data that is assuming human embodiment, but your agent, for example, might be a robot with a single arm. And finally, it must be matched to human expectations. So different users will have different expectations about how tasks should be performed and what constitutes appropriate goals and behaviors. These first three requirements we label as viable, meaning that they're required for the agent to even attempt to learn from these responses. To address these requirements, we develop STARS, which is illustrated below. It again begins as in the baseline by choosing and instantiating a prompt template, but rather than just retrieving a single response or many responses of a high temperature, the agent uses a search tree strategy to retrieve a breadth of high probability responses using beam search, which involves multiple queries to the language model. From this, it gets a set of responses that it then analyzes by evaluating through internal simulation and knowledge analysis in order to detect mismatches along those requirements previously discussed. After it detects mismatches, it tries to repair this knowledge via reprompting the language model, which also uses the process of the search tree again. Finally, the agent prompts the language model with the set of candidates that it has deemed to be viable to select a particular option. When user oversight is available, the agent will also ask the user to confirm or disconfirm the goal retrieved before using it. And this is to align with the final requirement, matching human preferences. Once the human has confirmed a goal, the robot will learn from that goal and use search capabilities to find a solution. Now we'll go into a little bit more detail on the analysis and repair process. Consider this initial response from the language model that the robot is going to analyze. The goal is that the ceramic bowl is in the dish rack and the dish rack is in the cabinet. What the agent will do is simulate learning from the response to proactively identify issues using multiple sources of knowledge. Sources of knowledge coming from language, from the situation, and from its knowledge of affordances and embodiment. So first, it will parse the response using its language knowledge and evaluate for language mismatches and unknown terms. Then the agent will ground references to objects in the environment and identify ungrounded refs. In this case, it is able to ground ceramic bowl and dish rack, but it can't ground cabinet to anything that it is currently perceiving. Then, using affordance and embodiment knowledge from the environment and its semantic memory, it will analyze whether there's any mismatches of affordances, analyzing basically if the goal is achievable. So in this case, when it sees that the dish rack is in the cabinet, from this it infers that the dish rack must be moved. But in searching its affordances, it notices that dish rack is not a grabbable object because the robot is only capable of picking up smaller sized objects. So the detected mismatches here are the affordance mismatch on the dish rack and the grounding mismatch on the cabinet. And so from here, the agent can attempt to do repairs on this response by saying no, it cannot see a cabinet, or no, the dish rack is not grabbable. Here we show the repair process, which again reuses the search tree process from the other part of STARS. So here's another example where we're prompting for a apple core that we see on the table where we're trying to learn to tidy the kitchen. And the search tree process will return a bunch of responses that the agent, through analysis, will be identified as viable, here highlighted in green, or highlighted in red that they have some mismatch that requires a repair. And so for this middle response, the goal is that the apple core is in the bin and the bin is closed. The bin in this environment doesn't have a lid, so it identifies the mismatches that the bin cannot be closed and re-prompts the language model with this added information. And so here we get back a new response. In this case, it's a duplicate, but it did remove the offending clause that the bin was closed. Similarly, it can't see a cabinet, so it re-prompts the language model here and gets new responses for the apple core in different locations. We evaluate STARS on an interactive task learning agent. Interactive task learning is where agents learn in real time all aspects of a task from natural interactions that are real time online, showing one-shot learning and accumulating knowledge over multiple tasks. In particular, we're evaluating on an interactive task learning agent implemented in SOAR that has been embodied in many different robotic platforms and simulators and has learned from mobile robot tasks to many different games and puzzles. Here we show a demonstration of an interactive task learning agent using STARS. Below here is the simulator with a robot in a kitchen, and above is a chat dialog window that the user and the agent can interact in. So first, the instructor gives the task to tidy the kitchen and instructions to repeat the following task while objects are on the table. And the task will be to clear objects that are on the table. And rather than asking the instructor to provide goals for these objects, it will use STARS to learn goals for each of these objects, starting with the plastic fork. And so using the templates and instantiating it with information with the plastic fork, it retrieves through the search tree a number of responses. It then analyzes these responses, determine which are viable and which are unviable, and for the unviable goals, the reason of the mismatch. Using these mismatches, the agent will then attempt repairs, and from these repairs, it will get a new set of viable goals, for example, that the plastic fork is in the sink. Finally, from the candidates that it determines to be viable, the agent will prompt the language model with these options, and in this case, the language model selects that the goal is that the plastic fork is in the drawer and the drawer is closed. And because we're using oversight here, the agent will present this option to the instructor. In this case, the instructor is going to reject this goal because they have an assumption that plastic forks should be assumed to be dirty if they're on the table. The offending goal will be removed from the selection options and the selection will repeat. In this case, the agent is going to offer that the goal is that the plastic fork is in the garbage, which the instructor accepts. Immediately, the agent begins to search, and using its planning capabilities, it's able to find a sequence of steps to achieve the goal. And at this point, this process will repeat for the other objects that it sees on the table. We performed experiments on 3 different tasks: tidying the kitchen, organizing an office, and storing groceries, showing improved performance with stars for each task. On the right is a figure from the paper for the tidy kitchen task. Please refer to the paper for more details. With the baseline template-based prompting strategy, the agent only achieved 52% task completion for the tidy kitchen task. Task completion meaning the percentage of objects that were in the correct final state and position. With stars, the task completion for tidy kitchen increases to 77%, increasing for all the other tasks as well. When stars is using oversight, this task completion rises to 100% for all tasks, with a great reduction in the required user effort. And further, this user effort shifts from providing goal descriptions, which is required when the language model doesn't provide a correct goal, to simple confirmation of language model provided goals. In conclusion, issues with language models, like hallucinations and relevancy, can limit their utility as a knowledge source, particularly for embodied agents. But the STARS agentic approach of retrieving, analyzing, and repairing a breadth of language model responses can help make them a reliable knowledge source for learning. This is by the cognitive agent providing context and verification to align the responses with learning requirements. In the experiment, STARS improves task performance and reduces required human oversight. For future work, we're looking at evaluating stars on different learning targets like grounding knowledge and different task environments, and exploring improvements to language model selection, especially via the use of additional context that could be provided by the user. Finally, I would like to acknowledge our funding from ONR. Thank you very much.